welcome back to our YouTube channel. As you know that we are studying about the integral transform, in which we have studied the first chapter, that is beta and gamma function, and in the previous lecture we have seen the definitions and some properties and basic to advanced level problems based on beta and gamma function. Now, after that we have studied about the Laplace transform, in which we have seen a function, how to take the Laplace transform of that function, what condition remains satisfied by that function to get Laplace transform of that function, and after that we have seen the method Laplace transform of basic functions such as 1, t raised to n, Laplace transform of e raised to at, Laplace transform of sin at, cos t, correct? And after that we have seen the properties based on that function, based on the Laplace transform, and by using that properties we have solved so many examples in previous lecture. Today we will go to find the Laplace transform of some example. We are studying about the Laplace transform. So Laplace transform. In which we have to find Laplace transform of t square cos t and y, Laplace transform of F of, where f of t is t square cos t. Correct. Since we know that whenever we have a function in which t raised to n is in multiplication with that function, we use the theorem t raised to n f of t is equals to minus 1 raised to n d by dsn of f of s, where capital F of s indicates the Laplace transform of f of t. F of t, whatever the f of t is, first of all we have to find the Laplace transform of that f of t. Then the power t raised to n indicates how many times we have to differentiate that function. So here we have t square cos t. So Laplace transform of t square cos t, correct? And we have minus 1 raised to n t, sorry, 2, because we have t square, d square by ds square, and Laplace transform of cos t is s upon s square plus 1. It is the Laplace transform of cos t. So we have d square by ds square of s upon s square plus 1. Now since we know that the square of minus 1 is 1, so there is no need to write 1 there. Then we have to differentiate twice to s upon s square, so we can write it as d by ds of d by ds s upon s square plus 1. Since we know that du by v form, we will take v outside, then differentiation of u minus taking u outside, differentiation of v upon v square. It is the formula whenever we get a function in u upon v form, we will differentiate by using this formula. So we take d by ds as it is, then s square plus 1, since it shows the value of v, taking v outside, differentiation of s with respect to s, minus taking u outside means s outside, differentiation of s square plus 1, and in the denominator s square plus 1 bracket square. We have this formula to integrate, differentiate s upon s square plus 1. Now we will try to simplify that x expression d by dx as it is. Differentiation of s with respect to s, we will get 1. So s square plus 1 as it is into 1 minus s as it is, and differentiation of s square plus 1 will gives us 2s. Correct. Now x square plus 1 as it is, so we will leave it as it is. Then we can write it as d by dx of s square plus 1 after multiplying by 1, there is no change. We will get minus 2s square, s square plus 1 bracket square. Correct. After solving this, we will get d by dx of 1 minus s square upon s square plus 1, and we have one more derivative to solve this expression. Again we will get u upon v form, and it is little bit complicated, so go with very care. Taking s square plus 1 bracket square outside, I am going to directly differentiate the function, and we will get minus 2s because we have very less space to write all steps. So we are taking s square plus 1 bracket square outside, differentiating this 1 minus s square, we will get minus 2s. Then taking 1 minus s square outside and differentiating this term s square plus 1 bracket square, so we will get 2 s square plus 1. Correct. Then 2s. Yes. No, sorry. 2s upon s square plus 1 bracket square. So here we have s square plus 1 common. We can take it outside. S square plus 1 taking outside, we will get s square plus 1 minus 2s minus 2 to the 4 s 1 minus s square plus 1 we have already taken outside upon s square plus 1 raised to 4 s square plus 1, and these 4 get cancelled, we will get 3 here. So we will write minus 2s cube minus 2s minus 4s minus 4s minus 1 will become plus 4s cube. Correct. And this becomes s square plus 1 cube. Now we have 2s minus 4s minus 2s cube and plus 4s cube. We will get 2s cube minus 6s upon s square plus 1 bracket cube. It is the Laplace transform of t square cos t. Correct. Now they asked us to find Laplace transform of f dash of t. Now by using differentiation method we can solve, and by using simple differentiating the function we can solve this expression also. By both methods it is correct, but if it is given that find the Laplace transform of f dash of t by using differentiation method, we have to solve by using that formula. Laplace transform of f dash of t is equals to s upon Laplace transform of f of t minus f of 0. By using that formula, if we are given a solve by differentiation method, correct, and if it is not given, then we can find differentiation of these functions first and directly differentiate the function, directly taking the Laplace transform, we will get the result. We will try both the method to check our result is correct or not. So I think you have understood all these steps. Now I am going to solve f dash of t. Laplace transform of f dash of t. Oh, sorry. F dash of t, and we have Laplace transform of f dash of t means f of s is equals to this 2s cube minus 6s. Right? Because we need for this. Now since we know that Laplace transform of f dash of t is equals to s f of s, or we can say that f Laplace transform of f of t minus f of 0. Correct? And we can write it as s f of s f of 0. As it is, f of s means Laplace transform of t we have already 2s cube minus 6s upon s square plus 1 cube. We have this, and f of 0. If f of t is equals to t square plus cos t, if we put t is equals to 0, 0 square becomes 0, 0 into cos 0 becomes again 0. So we have Laplace transform of f dash of t is equals to s into 2s cube minus 6s upon s square plus 1 bracket cube. We have two different answers for that. Laplace transform of f of t is equals to 2s cube 6s upon s square plus 1 cube, and Laplace transform of f dash of t is equals to just multiplied by 2s raised to 4 minus 6s square upon s square plus 1 bracket cube. We have all these results. Now by using these results, we will try to solve by using differentiating the function. Since f of t is equals to t square cos t here, if we differentiate, we will get, again, t square outside, differentiation of cos t becomes minus sin t minus plus taking differentiation of t square, that is 2t cos. Correct? Now using Laplace transform of f dash of t will give us minus t square of sin t plus 2t cos. Now we are in trouble. Why? Because we have to find sin of t, then twice the differentiation of sin t, then differentiation of cos t, because we have to raise to 1, and after getting all these things, we will compute and simplify this term by using addition and subtraction, and after doing all these things, we will get the result. So we will try to solve this example in next lecture. Till then, thank you. Bye.